Here's a puzzle. The 90-degree rotation matrix with entries 0, negative 1, 1, and 0 has eigenvalues plus I and minus I, purely imaginary numbers. But this symmetric matrix, where the off-diagonal entries match, has eigenvalues approximately 1.38 and 3.62, perfectly real. Both matrices have real entries, yet the moment we impose symmetry, every eigenvalue snaps onto the real number line. Symmetry has a secret. Let's chase it down. Let's start with the eigenvalue equation. A times x equals lambda times x. We're going to allow lambda and x to be complex. That's the whole point of this proof. We need to show that even if we let them roam through the complex numbers, the symmetry condition, A-transpose equals A, will drag lambda back to the real line. So here's our setup. A is a real symmetric matrix, lambda is a candidate eigenvalue, possibly complex, and x is its eigenvector, nonzero, also possibly complex. Our goal is to prove lambda must be real. Our first move is to take the complex conjugate of both sides of the eigenvalue equation. Conjugation distributes nicely over products and sums, so ax equals lambda x becomes a bar times x bar equals lambda bar times x bar. But notice, A has no bar over it. That's because A is a real matrix, so A bar is just A itself. We get, cleanly, a times x bar equals lambda bar times x bar. As a free bonus, this single line proves a famous fact. Complex eigenvalues of real matrices always come in conjugate pairs. If lambda is an eigenvalue with eigenvector x, then lambda bar is also an eigenvalue with eigenvector x bar. But our target is bigger than that. We don't just want lambda bar to be some eigenvalue. We want to show lambda actually equals lambda bar, which would force lambda to be real. Second move, transpose both sides. Remember, the transpose of a product reverses the order, so x bar transpose times A transpose equals lambda bar times x bar transpose. Now comes the key step. A is symmetric, which means A transpose equals A. Replace it. We get x bar transpose times A equals lambda bar times x bar transpose. Pause on this. Symmetry is the only ingredient that lets us swap a transpose for A. Without it, the proof dies right here. With it, lambda bar now sits on the left of A, while lambda still sits on the right. That asymmetry is exactly what we'll exploit next. Now let's squeeze both equations toward the same quantity. Start with x bar transpose A equals lambda bar times x bar transpose, and the right multiply both sides by x. The left side becomes x bar transpose AX. The right side becomes lambda bar times x bar transpose s. Independently, take the original equation ax equals lambda x and left multiply both sides by x bar transpose. The left side is x bar transpose as, exactly the same expression as before. The right side is lambda times x bar transpose x. Now we have two expressions that both equal x bar transpose as, so we can set them equal to each other. Lambda times x bar transpose s equals lambda bar times x bar transpose x. We are one step away from the punchline. We want to cancel x bar transpose x from both sides, but we can only cancel a quantity if it isn't zero. So let's see why x bar transpose x is never zero for a non-zero vector. Write each component x sub k as a sub k plus I times b sub k, splitting it into real and imaginary parts. Then x bar sub k times x sub k is a sub k minus ib sub k, multiplied by a sub k plus ib sub k. That's a difference of squares pattern, and it simplifies to a sub k squared plus b sub k squared. Now sum over all components, we get x bar transpose x equals the sum of a sub k squared plus b sub k squared. This is a sum of squares of real numbers, so it's strictly positive whenever x is non-zero. Geometrically, this is the squared length or norm squared of a complex vector. For a quick example, take x equals 1 plus 2i, 3 minus I. The first component contributes 1 plus 4, that's 5. The second contributes 9 plus 1, that's 10. Total 15, which is positive as expected. Why does the bar matter? Let's see what goes wrong without it. Take the vector x with components 1 and I, try the naive x transpose x. You get 1 times 1 plus I times I, that's 1 plus negative 1, which equals 0. So a non-zero vector ends up with 0 squared length. That's a disaster. Now try x bar transpose x, where we conjugate the first factor. The conjugate of I is negative I, so you get 1 times 1 plus negative I times I. Since negative I times I is plus 1, this becomes 1 plus 1 equals 2. The conjugate flips I times I from minus 1 to plus 1. That is the whole reason complex inner products must conjugate one factor. Back to the punchline. We have lambda times x bar transpose x equals lambda bar times x bar transpose x. We just proved that x bar transpose x is a positive real number, so we can safely divide it out from both sides. What remains is the clean statement. Lambda equals lambda bar. Now a complex number equals its own conjugate only when its imaginary part is 0. Therefore, lambda must be real. Done. The symmetry condition, A transpose equals A, forced any candidate eigenvalue, no matter how complex it pretended to be, to land on the real line. Let's review the architecture of the proof. It rested on 3 engines. 1. We conjugated the equation and A didn't change because it's real. 2. We transposed and A transpose collapsed back to A because A is symmetric. That was the key step. 3. X bar transpose times x is a positive real number, so we were allowed to divide. Knock out any one of these supports and the whole proof breaks. Now let's generalize. If A has complex entries, then A transpose equals A is no longer the right condition. The natural condition becomes A equals A bar transpose, the conjugate transpose. Matrices satisfying this property are called Hermitian. For example, the 2 by 2 matrix with entries 2, 1 plus I, 1 minus I, 3 is Hermitian. The off-diagonal entries are complex conjugates of each other, and the diagonal entries are real. Now run the exact same proof, but with A bar transpose replacing A transpose throughout. The conclusion is identical. The eigenvalues are real. So real symmetric matrices are simply the real special case of Hermitian matrices, and as a bonus, both classes also have orthogonal eigenvectors. Why should you care? Symmetric and Hermitian matrices appear everywhere real measurements live. Covariance matrices in statistics are symmetric with real variances. Quantum mechanical observables are Hermitian with real measurable values. Graph Laplacians are symmetric with real frequencies. Hessian matrices of second derivatives are symmetric with real curvature. In every case, the algebraic condition A transpose equals A, or its complex cousin, is what guarantees the numbers you compute are numbers you can actually observe. And there's a bonus we didn't prove. Eigenvectors of a symmetric matrix corresponding to distinct eigenvalues are automatically orthogonal. So a symmetric matrix doesn't just give you real eigenvalues, it gives you a perpendicular set of axes along which the matrix simply scales. That's the spectral theorem, and it's the foundation of principal component analysis, normal mode analysis, and the quantum measurement. The takeaway, symmetry isn't just aesthetic tidiness. It's the algebraic fingerprint that keeps eigenvalues grounded in reality. Whenever you see A transpose equals A, you know without computing anything that the spectrum lives on the real line, and the eigenvectors form a clean orthogonal frame. One condition, 2 enormous consequences.